Namaskar and a warm welcome to this series of lecture. Myself, Dr. Prain Kumar Sahu, belonging to Government Sama Prasad Mukherjee College, Sitapur, Chhattisgarh, India. And this is a lecture pertaining to M.Sc Mathematics, second semester of Sant Gahira Guru University, Sarguja, Ambikapur, Chhattisgarh. And the paper is first paper, Advanced Abstract Algebra Part 2. And the unit is 30 minutes. And this is my fifth lecture on this 30 minutes. And the topic of this lecture is two very important topic in third unit, algebraically closed field and perfect field. So let's start the lecture. First of all, we will see the point that we will discuss in this lecture. In this lecture, we will define algebraically closed field and perfect field, and we will see some example questions and theorem based on these two. So first of all, what is algebraically closed field? A field K is said to be algebraically closed if every non-constant polynomial in K of x splits completely in K. Means it has all its root lies in K. Now, we can say for any polynomial f of x in K of x, all the roots of f of x must lie in K, then only it is algebraically closed. Now, we can see that rational is not algebraic closed field because there is a polynomial fx is such that x square minus 2 which lies in q of x, but it has a root 2 which does not lies in rational. Similarly, real number are also not algebraically closed because there is a polynomial fx is equal to x square plus 1 which lies in r of x, but it roots iota which is under root minus 1 does not lies in real number. And from the famous fundamental theorem of algebra, you know that the complex numbers is algebraically closed field. Now, there is some theorem. An algebraically closed field can't be finite. We shall prove this result by contradiction. Suppose we have an field K which is a finite algebraically closed field, such as K is equal to a1, a2 all the way up to an. Now consider a polynomial fx is equal to 1 plus x minus a1 times x minus a2 all the way up to x minus an. Clearly it is a polynomial over K because its coefficient 1 and a were all lies in K. Now it has all its roots in K because K is algebraically closed, then by its definition. But none of the a1, a2 all the way up to an is a root of this fx, which is a contradiction that K contains all the roots of given polynomial f. So f can't be finite. Let's prove our theorem. Now there is another theorem which says that if f be an algebraic extension of some algebraically closed field K, then f is equal to K. Both of them, we have an equality here, both of these are same. What we are given, f is extension of some base field K. So from the definition of extension, what we have, K is subset of equal to f. Now to prove f is equal to K, we have to prove f is subset of K. Then by using this 2 we can show f is equal to K. Now for this we start with an alpha belonging to f. Then this alpha is algebraic over K because f is algebraic extension. We have given that f is an algebraic extension. So there exists a polynomial fx over K such that f of alpha is equal to 0. This is from the definition of algebraic extension. So this implies alpha is a root of f of x. As fx over K and K is algebraically closed, so by definition it has all its roots in K. So alpha lies in K. What we have taken alpha belongs to f, and what we have, alpha belongs to K, means f is subset of K. And from equation 1 K is subset of A, then by using equation 1 and 2 what we have, f is equal to K. So this proves our theorem. Now we will see what is a perfect field. A field K is called a perfect field if all finite extensions of K are separable. Now let's see then an example of field which is not perfect. Means we have a field f of p, the field of rational in an unknown t, then this is not perfect. Why? Because f of x is equal to x to the power p minus t lies in f of pt. Then by applying Einstein criteria, irreducibility criteria in unique factorization domain f of pt, so which is subset of f of pt and the prime t in it. Now alpha to the power p is equal to t, and what we have x to the power p minus t, then we will have x minus alpha to the power p. So we have multiple roots, so it is not a perfect field. Now you already know what is the characteristic of a field. Let's revise it. Suppose we have a field f plus and dot, then the least positive integer n if exists such that n dot 1 is equal to 0, then it is called the characteristic of a field. If there exists no integer n such that n dot 1 is equal to 0, then we said f is of characteristic 0. The example of this are rational and real number which has characteristic 0. So there are two remarks which says that characteristic of a field is either 0 or a prime number. Finite field have characteristic p and infinite field have characteristic 0. Now there is a theorem which says that an algebraic extension of a perfect field is a separable extension. Let we assume that K be a perfect field and F be an algebraic extension of base field K. Then we have to prove F is a separable extension of K. For this, let A lies in F. Then F is an algebraic extension of F of K given. So A is algebraic over K, means then so A adjoint to K over K is finite. Then implies A adjoint to K is finite extension of K, but K is a perfect field given to us. Then K of A adjoint to K is a separable extension of K, which implies A is separable over K. But here we have taken A as arbitrarily, so every element of F is separable over K. So F is a separable extension of K. This proves our theorem. Now there is another theorem which says that if there is any field of characteristic 0, then it is a perfect field. Now we are taking K be a field of characteristic 0 and let F be a finite extension of some base field K. Then we have to prove that F is perfect. We have to prove F is a separable extension of K. Now as F is a finite extension of K, it is given to us. Then F is an algebraic extension of K. So for any A which lies in F is algebraic over K, there exists a minimal polynomial P of x of A over K such that Px has all its roots distinct as K is characteristic 0. So Px is separable over K, and then implies A is separable over K, but A is arbitrary. We have taken A arbitrary, so F is separable extension of K. So this implies K is a perfect field by using last property. Now we have to prove an important theorem which says that any finite field is perfect, or any algebraic extension of a finite field is a separable extension. Now we are taking K to be a finite field with characteristic K is equal to P, where P is a prime number. Now let F be an algebraic extension of this base field K. Then we have to prove that F is a separable extension of K, or we have to prove K is a perfect field. For this, let A lies in F. A is arbitrary element we are taking. Then A is algebraic over K because F is algebraic extension of K. So there exists a minimal polynomial P of x of A over K. Now we claim that P of x is separable. Now we will prove this by contradiction. Let if possible suppose that P of x is inseparable. Then implies Px lies into x to the power P adjoint to K. Means P of x is equal to alpha 0 plus alpha 1 x to the power P plus alpha 2 x to the power P to the power 2 all the way up to alpha n x to the power P to the power n. Here alpha 0, alpha 1, alpha 2 all the way alpha n will lie in K. Now as we know, alpha to alpha to the power P is an automorphism. So what we have, alpha naught will be beta naught to the power P, and alpha 1 will be beta 1 to the power P, alpha 2 will be beta to the power P, all the way up to alpha n is equal to beta n to the power P. So Px will be beta naught to the power P plus beta 1 to the power P x to the power P plus beta to the power P x to the power P whole square plus all the way up to beta n to the power P x to the power P to the power n. So Px will be beta 0 plus beta 1x plus beta 2x square plus all the way up to beta n x to the power n to the power P. So clearly Px is reducible over K, which is a contradiction as Px is a minimal polynomial which is always irreducible. So Px is separable. From contradiction we have proved x, Px is separable, means F is a separable extension of K. Means here we can say K is a perfect field. So this proves our theorem. So that's all for this lecture. In this lecture we have discussed two very important topics, algebraically closed field and perfect field. So that's all for today's lecture.